Good afternoon, everybody. We're going to be finishing out the notes on simple harmonic motion. So this may take a little bit of time. We're picking up at the top of the fourth page, and we're looking at a graph of the position versus time at different points for a mass on a spring in simple harmonic motion. So this is a vertical spring with a mass on it, and while it's at rest, it would be at equilibrium position. But to start the oscillations, we pull it down to release it. When you pull it down, the point at which you release it becomes the amplitude for the motion. And that could be whatever position you choose, as long as you don't exceed the elastic limit of the spring. So in this case, we have pulled the mass down to 0.2 meters. We release it, and it accelerates upward to the equilibrium point. Notice this is a curve. The acceleration, the velocity is increasing, but the acceleration itself is decreasing because the net force and the spring force is changing. So when we reach equilibrium, the net force becomes zero. So acceleration at this point becomes zero, as well as the position. We take the equilibrium position to be zero. And then the mass will continue upward, and the spring force will slow it down to a stop at the top where the velocity is zero. You're just changing direction there. The acceleration will be a maximum. Then you accelerate back down to equilibrium, where again the velocity is at a maximum because it's steepest right here, but the acceleration is zero. Then you decelerate because now the spring is pulling back on the mass instead of pushing it. It's pulling it back right here. So it's going to slow down to a stop again. Zero slope, zero velocity, because this is a position time graph. The slope is the velocity. And it just keeps going through those cycles. In fact, from here to here, this is considered one cycle. You've gone all the way up and you come back all the way down. So you've gone from 0 to pi over 2, pi, 3 pi over 2, and 2 pi radians, okay? And it just keeps repeating those cycles over and over. Now, if we are given that the mass on the spring is 1 kilogram and that the period, as you can see here, is 2 seconds, we want to find a number of things. We want to find the amplitude, the frequency, the angular frequency or angular velocity, the K constant of the spring, the maximum velocity that it will have, and the maximum acceleration that it will have. So let's start with some of the easier things first. Simply put, we can get the magnitude of the amplitude from the graph itself. The amplitude, again, is set by you when you release it. So the mass is 0.2 meters below equilibrium, and it will travel that same distance above equilibrium. So the amplitude is also 0.2 meters. Now, the period we said is 2 seconds, and all you have to do is look on the graph to see the period. You've got the time here. Just look at from one point to the very same point that it comes, when it comes to that very same point again. Look, 2 cycles. Goes all the way up, comes all the way back down. That takes 2 seconds. Not 2 cycles, sorry. 2 cycles for 2 seconds for 1 cycle. I'm all twisted. All right, so the period is 2 seconds. Now, getting the frequency is going to be very easy. We already know that frequency is the perfect reciprocal of period. So if the period is 2 seconds per cycle, then the frequency would have to be 1 cycle for every 2 seconds, or 0.5 hertz. Okay? Next, we're asked to find the angular frequency. That is also easy. The angular frequency is related to the linear frequency by the product of 2 pi. 2 pi f is the angular frequency. So let's see, where do I have it? I'm trying to keep some stuff covered. There it is. Okay. So we get 2 pi f, and we multiply that out, and we get 3.14 radians per second. Okay. Now, knowing the angular frequency and the amplitude, we can work on k, v, and a, the maximum speed and the maximum acceleration, as well as the spring constant. Let's start with the spring constant. Now, where in the world did I get this little formula from? Okay, well, we know that the angular frequency is equivalent to the square root of k over m. So to solve for the k, first we square everything, and then, because we're dividing k by m, we have to multiply it on the other side. Okay? All right. So now, stick in your angular frequency that you just found, square it, multiply by the mass, you get 9.9 newtons per meter. Okay, now that we have those, let's talk about the maximum velocity and maximum acceleration. If we look back on our graph, we said the maximum velocity is right here at equilibrium, where the acceleration drops to 0. That doesn't mean the object stops. That just means the velocity can't change at that point. And therefore, that's the maximum it's going to have, because once you go past it, it's going to start slowing down. So, we're going to find the velocity when it's a maximum right here. The acceleration is a maximum when the velocity is a minimum. This is where the net force is the largest, so that's where the velocity is changing the fastest. It's going from non-zero in one direction to 0 to non-zero in the other direction. So that's a rapid change in velocity, therefore a very large acceleration. All right, so now how do we do that? Okay, well, the velocity is a maximum when the cosine of the angle drops to 1. So we get a times w times the cosine of cosine of 0, and you get 1. So a times w is 0.2 times 3.4 radians per second. You get 0.628 meters per second. All right, now the acceleration is a maximum at 180 or 270 degrees, which corresponds to the sine of 90 or 270. The sine of that is 1. So you get the maximum acceleration is a omega squared. In fact, if you remember the other day, we wrote a little chart. Let me show you where we wrote that before. On the top of the 3rd page, we wrote a little chart. Okay, and we said the location where these are a maximum. Okay, the maximum position is at amplitude, and the minimum is at equilibrium. The maximum velocity is 0, minimum at amplitude. It's maximum at equilibrium. The acceleration is a maximum at amplitude, but it's minimum at equilibrium. So we can use these for the maximums. We just have to remember where they're located on the graph. Amplitude for position and acceleration. Equilibrium for velocity. Okay? So now, and I made a boo-boo on the unit, so I tried to fix it there. There you go. Now you got it. All right, so if we say a omega squared, we get 0.2 meters times 3.14 radians per second, and square that quantity. So the acceleration right here is going to be 1.97 meters per second squared, even though the velocity is 0. It's the direction of the velocity that's changing right there. So that's where we have the maximum acceleration. All right, so there's looking at the little ways you can use some of those little formulas. Now, let's talk about energy of the spring. I have put on, in your folder tomorrow, you will see a flipping physics video on energy of a spring. So let's just take a quick look at it though. Whenever you have a spring stretched, where'd my little spring go? It keeps rolling around and I keep oh, here it is, found it. Okay, so if you stretch a spring, the spring pulls back against your stretch, and therefore it has stored in it what we call elastic potential energy. If you compress the spring, it pushes out against you with a restoring force. So right now, with it compressed, again, it has elastic potential energy. It has the potential to do work if you release it to restore itself. All right. So we still use a U for potential energy, but now we put an S on it. I just for spring potential energy, okay? Also called elastic potential energy, always measured in joules like other energies. But it's the energy stored in a spring due to the compression or stretch. To find the elastic potential energy, you say 1/2 times the K constant of the spring times the position, or the stretch, sorry, not position, the stretch squared. Remember, stretch for a spring is a difference in lengths. Okay? So if we look at masses on springs, they can have mechanical energy depending on their orientation. Why do I have some sideways stuff here? Oh, well, we'll get to it in a minute. But right here, if we look at mechanical energy, a mass on a spring that's oscillating, and if it's a vertical spring, it can have translational or linear kinetic energy for the mass as it goes up and down. All right, it can have gravitational potential energy, because if it's a vertical spring with a mass on the end, the mass will be going above, up and down, changing position above your 0 point for gravitational potential energy. Then, as the spring compresses and stretches alternately, you can also have elastic potential energy. So you have 1/2 mv squared for the translational kinetic energy, mgh for the gravitational potential energy, and 1/2 kx squared for the elastic potential energy. Okay? What if it's, however, a horizontal spring with a mass on the end on a frictionless surface? In that case, you wouldn't have gravitational potential energy because the mass is moving horizontally. It's not going up and down. So if you set the 0 height for the gravitational potential energy to be the height where the spring is located, then it never has any gravitational potential energy. So we just have translational kinetic energy and elastic potential energy. 1/2 mv squared plus 1/2 kx squared. Okay? All right, and I did, oh, that's what this is. These are these two diagrams. Here is the vertical spring, and I'm showing how from equilibrium, if you set the height of the mass at the bottom amplitude, then you'd have a potential energy at equilibrium and a greater potential energy at the top amplitude. And at these points, you would also have different amounts of kinetic energy. Well, if you'll think about it, here and here, the kinetic energy would have to be 0 because this is where the mass stops and changes direction. So you'd have gravitational potential energy at these 2 points. Well, maybe not that one, but you'd have it at this point, but you wouldn't have any kinetic energy. You would have elastic spring energy, okay? Here is a picture of a horizontal mass on a spring. And it's showing right here that you can have kinetic energy in the center, all right, where the mass is moving at its maximum velocity, but you wouldn't have kinetic energy where it stopped to change direction. You would have spring energy at the two amplitudes because that's where you have the maximum compression and the maximum stretch. But as it goes back towards equilibrium, the spring energy decreases until it's zero at equilibrium, because at equilibrium, it's no longer stretched or compressed. It's its original length. So no spring energy right here. Okay, if we look at this example, you have a block at rest on a horizontal frictionless surface. Okay, it's attached to a horizontal spring whose spring constant is 124 newtons per meter. The block is shoved parallel to the spring axis and given an initial speed of 8 meters per second while it's initially unstrained. What is the amplitude of the resulting simple harmonic motion? Okay, for this example, we're going to start with conservation of mechanical energy. All right? So what we want to do is look for the maximum stretch. That's where the amplitude is. Remember, that's also where the kinetic energy is zero and you have maximum spring energy. So let's take a look. If we start out with conservation of mechanical energy, there is no gravitational potential energy, only linear kinetic and elastic potential energy on both sides. All right, so initially, when it's unstrained, but it has a speed of 8 meters per second, you're going to have kinetic, but no elastic potential. On the other hand, at the amplitude, you have no kinetic energy, all elastic potential energy. Okay, because that's where we want to find the amplitude. We know at the amplitude, that's where the kinetic energy is zero. So all of this has been converted into elastic potential energy. So now it's basically plug and chug. And for the answer, notice I did stick A in for X because we are looking at the amplitude, and that is the maximum stretch. We get 0.1 meters for the amplitude for this simple harmonic motion. Okay? All right, you can always pause it right here and copy that. Now, we only have a little bit more, so I want to go ahead and go through it. Now, this example next is quite involved, so I'm going to go through it, but I would suggest what you do is that you pause the video, copy the information down, and then go through the explanation. We have a mass of 2 kilograms, and it's hanging from the end of a vertical spring at rest initially, we will assume. The spring constant is 50 newtons per meter. The object is then subsequently pulled down 0.2 meters and released from rest. Complete the table below, and we can say that the height at the point of release is 0, and H indicates the distances above the point of release. So our position for 0 gravitational potential energy is going to be the bottom amplitude, where it's released. All right, so let's start right here. We know that at the release point where the height is 0, it starts from rest, so the kinetic energy at the beginning is 0. Okay? And the gravitational potential energy there is 0 because the height is 0. So all of our mechanical energy when it's released is just elastic spring energy. And we get 9 joules for that. How did I get that? Oh, I said 1/2 times 50 newtons per meter times 0.6 meters squared. And now you're thinking, well, wait a minute, where'd the 0.6 come from? Because it says you pulled it down 0.2 meters. Ah, but you got to remember, the spring was already hanging, the mass was already hanging from the spring at equilibrium. That means it was already stretching the spring. So before we can do anything else, we must first determine when it's in equilibrium, how far is the spring stretched at that point? Because from that point, you're going to pull it down 0.2 meters further. All right, so let me show you how I got that. Right here. The weight of the mass stretches the spring first. So I set the weight of the mass equal to Hooke's law. I solved for the stretch and I got 0.4 meters. So when it's just hanging there at rest, the spring is stretched 0.4 meters. Now you're going to grab the mass and pull it 0.2 meters down further to release it and start the oscillations. So 0.4 plus another 0.2 is 0.6 meters total. So that's where the spring energy comes from, and it's 9 joules. Now, here's a nice trick. We know that for ideal systems like this mass oscillating on a spring, mechanical energy is conserved. So if the mechanical energy is 9 joules at the bottom where we release it, then it's 9 joules at the other points as well. So I went ahead and filled those in, okay? All right, so now let's take a look. I drew a little picture right here to show what we have at each point. So at the bottom amplitude where we release it, the position is the amplitude, and we just determined it would have to be 0.6 meters and a height of 0. When it accelerates up and reaches equilibrium, that height would have to be 0.2 meters above the bottom because we only stretched it 0.2 meters. And the stretch of the spring at this point is 0.4 meters from without the mass to with the mass on the spring. Okay? This is what it is before you grab it and pull it down. Then, at the top amplitude, you're actually 0.4 meters above the bottom, and you're 0.2 meters above equilibrium. So 0.4 minus 0.2 is another 0.2. All right? Okay. So now we can use this information to fill in some of the other stuff. So let's look at the equilibrium position right here. At equilibrium, the mass is 0.2 meters above 0 meters. So we say mgh, we get 3.9 joules, and I'm sorry this thing keeps doing this. Okay. The elastic spring energy would be 1/2 kx squared, and since x is 0.4 at equilibrium, you get 4 joules. Okay? So now, look how I found the kinetic energy. Did we have to know the speed at equilibrium and say 1/2 mv squared? No, we didn't. All we had to do is realize we can only have a total of 9 joules. So 9 joules minus this 4 minus this 4, well, if you don't round and leave it 3.9, then what's left over to be kinetic energy would be 1.1 joules. Now, if you wanted to know the speed of the spring when it goes through the equilibrium point, you can use the 1.1 joules in the mass to find the speed. That's kind of cool. All right, going forward, let's now look at the position at the top, where the height above the bottom is 0.4 meters above the bottom, okay?